Welcome. This session is called What If Your Machine Could React to an Obstacle Before the Operator Sees It? So, short introduction. My name's Tim Conklin. I work with IFM, specifically with autonomous vehicles and obstacle detection type applications. And this is my colleague, Dr. Thorsten Kever.
Yes, hello from my side. I'm technical manager in the development over in Germany, so working on developing of the products for cameras and sensors, also for obstacle detection and other applications.
And for those of you who might not be so familiar with IFM, we're a family-owned technology company with 50 years experience in the world of automation. And so we do a lot of work in the on and off highway industry. And this is a major growth sector for us right now with, as you guys know, many of these applications are becoming a hot topic. So with that, we'll get started.
Yep.
So the whole idea of reducing blind spots on vehicles, it goes pretty far back. So here's a quote from a handbook in 1906 that talks about using a rear view mirror in a car. You know, something we now take for granted is this idea of, you know, blind spots in 1906. This was still a discussion point. And here's a good example. The first ever Indianapolis 500 winner, you can see they have a rear view mirror on board. And so I have a little video.
So you see that everyone is driving with two in the vehicle, and it's quite interesting. Even while going in circles here, they had a mechanic on board, and the mechanic has a second job just to check where are all the other participants. And just one guy, you see him here in the middle, he was driving alone, so sparing some weight on that. And he installed some mirror for him, so he could observe what's behind him. So quite interesting. Yeah.
He did pretty well, it turns out.
So he actually did win this. So, and in the next year, no one was driving with two persons anymore, but everyone had a mirror on his vehicle.
Yeah, so he had kind of an unfair weight advantage, right? But it's a small technological advantage that gave him the win.
Okay, so maybe coming more to our today's world. So I mentioned already our development and production is mostly in Germany. So in Germany for the businesses, we have what we call Employer Insurance Association. And they are, for example, if you're a garbage truck operator or in construction business, your employees are insured over this federal insurance company. So that means they make rules on operation safety, for example, so to prevent accidents. And they said on construction sites, drive-off, reversing, and, for example, for excavators, start of turning, one of main reasons for serious accidents involving workers on construction sites. So for them, one of the, let's say, main critical area in the working process is working with heavy machines and then the visibility for the operator. So they identified that, and one of their demands is in order to prevent such accidents, that the contractor in this case needs to make sure that the machines are equipped with appropriate technical systems in order to allow the driver to operate the machine in a safe way. Meaning, if you're the responsible person on the contractor side and it's your machine, you're responsible that the machine is equipped in a way that is the actual technology allows you, so that the operator can operate the machine safely and see, for example, that there are no blind spots. And there are some recommendation on that. If possible, direct line of sight for the operator is preferable. If not, then you can equip, for example, a camera monitor systems, but the monitor should be in direct line of sight for the operator. So it should be placed somewhere where he can see it easily. And you should see that the position of the cameras or mirrors should be in a way that you can't block it. So on a wheel loader, for example, that you can't block it by the bucket in front. So that are some recommendation and demands. So this is maybe we can go to the next. That are some requirements. They say I want to improve the visibility for the operator of the machine, and but if you think about that, that is necessary for him that he can react to the situations in the first place. So if he's not able to see if there is a person in the way or worker or not, he can't react. But the point is that the risk of accident in this case is still dependent on the skills, concentration, and physical state of operator. So if you have an experienced operator, he will be fine. But maybe if there is someone just new to the job, or I don't know, today maybe working on a smartphone in parallel, so it's still, the safety is still dependent on the operator itself. If you just have a vision system. So that means the trend is clearly to active assistance systems. In this case, active means I have some kind of sensors so that can detect persons or obstacles by themselves and can actively warn the operator visually or acoustically, and even block the machine or stop the machine. So this is a big step into more safety in this case, because even if the operator somehow is not up to the task in the second, the machine will stop by itself.
So here we kind of talk through, you guys are probably well aware of the different levels of autonomy, right? Level 1 through level 5. And the idea is, you know, level 0, you don't have any assistance. All the way up through the machine can drive itself at the push of a button, right? So we have a couple examples to show you guys about some of our real customer applications and where they fall into these different levels.
So on this level 0, there are some assistance system which fall under level 0 because as long as there is no, let's say, intervention into the vehicle itself, meaning you have a system in a car where you for example, for an ultrasonic sensor for back reversing, but it's not braking your car, but it's rather just showing something or beeping, then it's level 0 assistance. And one example for that could be in this, it's a wheel loader in a mine. So in this case, it could be a system where you have a 3D sensor and a 2D sensor here, and it works for the operator in a way that we see it later, that he's acoustically warned, and it's in France, and you see that he has a monitor with a live feed from the backward behind the vehicle. And it's in addition also actively measuring with a 3D sensor for objects. So it's the operator is warned acoustically and also by highlighting within the video stream, but the machine is not stopped. So it's still responsibility of the operator, but it's a help for him. So an assistance system. You see, it's in this case, it's detected. There's some distance shown, how far away the object or the person is, and you get the warning to that. So this is an example for this level 0 assistance without actively braking or doing something. So next step would be level 1, which is per definition of this SAE, which comes from the automotive business, which says that the driver assistance now interacts with the machine by, for example, braking, and the responsibility, but is still for the human driver. So maybe we can see the next example. That is one from a customer from us in Japan, and he's making compaction rollers, and it's very similar to what we saw before. But in this case, he connected it also to the brake. So basically it has 3 levels of reaction. One is, like before, we have a warning, acoustical, visually. we see some example on that. Level 2 means the machine is going slower, and level 3 means it's stopped if no reaction happens. So you see here, level 2 now, it's getting slower, and level 3, it stopped before it crashes into the person. And we see now some example. What's important for that, you know that it's always a bit tricky with a assistance system which interacts to the machine, so it must be reliable. So the operator is, if it has too many detections without cause, it won't be accepted by anyone. So it will hinder your efficiency. But you have some critical cases, for example, something coming in from the side, maybe small, it must react. But in other cases, like with a compaction roller, you sometimes need to go very close by a wall. So the system must be very precise on that. So you're allowed to drive by, but still need to react on a person. And lastly, the point you see, he's trying to accelerate. It's also blocking to start the machine if there's something in the way. So that is an example for, we have another example. It's a garbage truck company in Germany. And they also actively go to the brakes in case there's something. It's also critical because the machine is big and there are some accidents because they may approach not only trained personnel or workers, but it's on the normal streets. So in this case, it's similar. It's first a warning and then the brake is applied. So again here, we have, if the driver operator is not reacting, we can have a stop of the machine in order to prevent accidents. Okay, so the next point here would be that we do not only brake, but have some influence, for example, on the steering. So that is an example of a customer also in France, where he has some specific vehicles for grape harvesting. And the operator in this case has multiple tasks to do. So first he has to drive the vehicle along the grape lines. But secondly, he has to control the machine. For example, they are shaked for getting the grapes out, but he has to control how much is shaked and so on. So the advantage we have here is that the steering is taken over by the machine based on the 3D output. So it's an assistance system which allows him to concentrate on the control of the machine, that he can be more efficient in the way how he harvests the grapes in this case. So this is an example for the level 2, where also the let's say the steering is involved in the automatic control, but there's still an operator. Then there are the higher levels of autonomy here, where you see that we have the system as responsible here, and we have some driving modes which are fully autonomous, so you don't need an operator at all. And we have one example here. This is a customer in UK, and he's making the passenger stairs on airports. And the point here is that when the aircraft is on the parking position, that the passenger stairs are aligned to the door automatically. So you don't need you don't have to bring an operator here, that he goes to the plane and goes back. But this is done rather automatically. So this is an example. There's no operator, so everything is depending on the machine itself. But you have to keep in mind that this is a very specific driving mode. So it's not like that this stair can drive over the airport on its own, but it can rather do this one task. So going to the machine, docking and undocking. So it's an example of autonomous vehicle for a very specific task, very controlled in this case.
So we've showed you guys a few videos of our technology in action on customer vehicles, but we haven't really talked at all about how it works. So a little bit of the science behind it. Essentially, Our key technology is a 3D camera sensor where we measure time of flight based on infrared light, bouncing off the object and back. We do that calculation internally, and then the sensor does some post-processing on board and sends obstacle data or other data, for instance with the steering, into the control system. So there's limited downstream processing. It more so happens internal to the sensor. And Dr. Kever can talk a little bit more about the specifics of the chip and really what's going on under the hood.
Yeah. So this technology is basically, you could also call it LiDAR because it's in the last years often used, but basically it's the same principle. So we are actively sending out some signal, in this case infrared light, and what happens if it hits some object or something in the way, it's back reflected, so similar like a radar. And what happens is that you can measure the time the light needs for going to the object coming back, and out of this you get the distance. So you get an image of your surrounding with the as a 3D, so measuring the distance. And this technology, there's a daughter company of IFM called PMD Technologies, which are doing all the CMOS stuff for us and then making the actual images for this technology. And this is we are a majority shareholder, we have a minority shareholder, and it's also our partner with a fab for CMOS, is Infineon technology. And so we are working together with them on this technology. And we as IFM take then these images and put it into sensors and cameras and do all this software around it and try to solve application in different markets. And I already mentioned, so the basic principle of time of flight, like used in, for example, radar, is the principle you send out a short pulse in radar, for example, and you get some reflection back. And the distance then can be calculated out of the time the signal needs to come back. And this is, in our case, over the speed of light. You can calculate the distance. You see that light is quite fast, right? So 1 centimeter is roughly 67 picoseconds of time in this domain. And this is, for example, also used in every laser scanner. So this measuring principle. So PMD is a bit different in a way that we are not sending out a single pulse signal, but rather we have a long signal which is has a kind of modulation. So we are repeating at some specific frequency. In this case, mostly in between 5 and 100 megahertz, our light signal, and we are not looking at one time delay, but rather we are looking at the phase shift. So what we get here is we have a periodic signal and we get a periodic signal back, and there's a shift in the phase between them. And it works quite nice because it's much easier on the electronics to evaluate that instead of this very short times. So we need much less bandwidth, which allows us to build images like 2D images, which capture 3D, but we have a lot of resolution in that. Okay, so maybe that's a bit of detail, but the pixel itself is like a normal photodiode, but a bit special. So we have not one capacity which we are loading with the information, but two. And we are modulating with the frequency I showed you before, also the receive unit here. And so meaning that depending on the frequency, it's put into the two different capacities. And so the difference in the capacity, so a difference in voltage, is directly proportional to the distance, and that is what we evaluate. And you see the advantage here. We don't need to evaluate, try to measure very precisely a short time, but rather we got some voltage signal, which is easily to be evaluated. So this is a single pixel, and we build up a patch, so an imager with a lot of pixels, and get all the information at the same time. So we are trying to do this for many applications and markets. So with our daughter company, PMD Technologies, we try to address the consumer market. So typical applications here are gesture recognition, face unlock on the smartphone, for example, or some games, virtual reality stuff, and also automotive applications. It is mainly also gesture control of some like radio or something, and important driver awareness. So I'm checking if the driver is awake and is looking to the street. And then we have the industrial business. So we are here in the mobile market. So mainly collision avoidance, distance control, and other applications like line guidance we saw. But we are also addressing industrial automation and robotics as markets. And this is an example of the automotive driver awareness. So with a partner Infineon, you see what they do is that based on the 3D point cloud and the image you get from the imager, they can evaluate if the eyes are open, closed, where is the face, where I'm looking. And this is important for the higher level of autonomy, where in the car they say you're allowed to take the hands off the wheel, steering wheel, but you're not allowed to, for example, go to sleep because you need to take over the car within a few seconds. So this is one application. Then this is an example out of the industrial automation where, for example, dimensioning is a point where classically this is scanned the size of the packages, and this has some have some negatives here because it's rather slow. So you don't get a lot of you have to stop the parcels and wait until it's measured, and when we do it with the 3D imaging, it's much faster. So you can do a single shot image and you get all the information. So if the band is not too fast, you can even do it without stopping at all. And since you just need one sensor and it's all processed in the sensor itself, you can even have multiple positions where you check. So it's more dynamically usable. So a last application out of robotics. So we have a company here as a customer, which is called Bossa Nova, and they make for Walmart this kind of robots. They will drive through the Walmart and check the status of the shelves. So how many parcels are there left? And this is also there in every robot. There's a lot of 3D technology and 2D. So 3D shows you where the parcels are, and the 2D can read the barcodes. And this is fully autonomous. It's going very slowly to the supermarket and all the full day, and it's just scanning all the time on the shelves. So, but today we want to focus on the mobile applications. So this is for construction sites, for example. And there's maybe one point which is quite important. If you want to have it useful in a construction equipment, you need to be very robust. So it's a very harsh environment. So you have a lot of dirt, you have vibrations, shock, temperatures. That's why we specifically designed for this market, meaning temperature range -2 to +85. Protection rating, we know that machines are typically cleaned with high pressure cleaners, so you need to be able to withstand that with equipment. Then it's a typical operating voltage, so 12 or 24 volt battery, and shock vibration. So there are no moving parts, so we are quite robust against shock and vibration. And the other point is that the preferred interface is a CAN network. So we try to be able to solve the applications and do that based on CAN networks. So it's not necessary that you need an Ethernet cabling, because depending on the machine, if you have different parts and you have to put it together later, Ethernet is a bit difficult to cable. And that's also the reason why we try to put the full software and functionality within the sensor, meaning we don't need to transfer all the 3D and image data to some other place, but rather do the evaluation on board. So we can just transmit results via CAN. And we also have the, let's say, the E certification, meaning if you have a vehicle which is also driving to the construction site, for example, on a normal street, you need this to be allowed to use it there. Okay.
So, yep. Yeah, here we're going to have a little bit more fun with our scary garbage truck videos. But you can see we kind of talk through a few different use cases where these vehicles might, one, be approached for the person, right? Or on the other side, you might have some part of your road that you need to interact with, or a very small object, you know, maybe a child or something running out into the street in an unpredictable fashion. So, yeah, here's basically just a couple more examples to show you guys how we're, you know, implementing these auto stop features.
Yeah, and this is, in this case, it's a garbage truck, but it's the same application if you put it on a wheel loader or something else, or in compaction roller. So we try to explain what happens here. So I mentioned that before. So we have a sensor here which takes the measures 3D. We have real-time data capturing. This is calculated and calibrated. So what we get is a 3D point cloud of distance information. This is then filtered and clustered. So what we do out of this is we look at the pixels and do in the software, we segment them and put them together. So we are not interested in single pixels, but rather in objects. So what we do here is we cluster them to objects and we track the objects. And the object tracking means we get for every object information like where is the object, so at which distance, at which position, which height, but also which size has the object, and also the movement of the object, which is quite important. So is this object stationary or is this moving, and is this moving in my way, out of my way, and all this information is done here. And then we have a path where if we have the information on the vehicle, the velocity and the turning of the vehicle, we can put this two information together and see where is the vehicle moving and where are the objects moving. And by this, we can be more intelligent by predicting if there's a critical crash coming up or not. So this is also done here. This is a decision point. If there is the information, in this case, going to the brake, if a brake is necessary. And also video, so to show you which object here is critical and what's happening. So that is all done embedded in the system. So as a simple example, you see here what happens. So basically, we see in this example garbage truck, it's going backward with a constant velocity. And at some point, the sensor is picking up an object and it's tracked. But the situation is not critical because we calculate the time to collision, which is at the beginning rather large. And the distance is at this point getting smaller because there's no reaction. So at some point, we say the situation can become critical. So maybe we trigger an acoustical signal and optical. And then wait if the operator does something. And there's some point of no return where we say, if you don't react here, you will crash into the object. And at this point, there's a second signal to the brake directly. And you see then, in this case, the person will start, or the vehicle will stop braking. So we reduce the velocity, meaning that the distance now, the distance is getting closer, but at a slower speed. The time to collision at some point starts to grow because I'm braking, and in the end I will stop here, hopefully just in front of the object or person. Just an example how this may look like. I mentioned that if you know the velocity of the vehicle and the direction, you can predict where the vehicle is, for example, in 1.5 seconds. And you can see where the objects are. And in this case, you may see that there are critical cases where you see I'm on a collision course with an object, but other cases where, if, for example, I'm turning in a curve, and then this is not critical, even if there's an object. So if I I can react appropriately. Okay, so maybe also some examples.
Sorry.
Yeah, no problem. It's good. Just carry on. So I'm just going on. This is very similar to this is predicted where the vehicle is. You see, this is just a bit where it shows it's critical, and this is the object. And when the predicted position of my vehicle is at this is crossing a predicted position of an object in the same time frame, then it's critical. We see another example now. Here, it's basically not a vehicle I'm driving on, but in this case a person, and you see basically it's the same in both cases with a static object. And now comes an other case where when I drive behind another vehicle, but we are going at the same speed, it's not critical even. You see, we are here and we are not reacting because this vehicle is predicted to be here. So we are at the same speed. You see it even here, velocity in x is the relative velocity between us and the object is nearly zero. So it's not critical. Okay. So, this is an example. If this car is starting to brake, then you see that the velocity will get a relative velocity between our vehicle and the vehicle in front will increase, so it becomes more critical in this case, and then the sensor starts to react. So just one last example. It's an object comes from the side, which is also critical because it can run into your driving path, and you will see that in this case here, you see there's a short break because the object moves into the way but stops rather at the last moment. So that are some examples, and we try to visualize a bit more. So for reversing cases, so we played a bit with the drone that you can see what happens and then see what the system makes out of it. So if you drive backward, you get the distance and you get the warning here. And yeah, next. So you see that even a metal pole, which is a quite hard to see obstacle, is working fine. So it's detected here, you see, and you get the distance. So even in this case, it's working reliable. And same goes for closing in on a pedestrian. And you see that we can highlight the critical cases in different ways. And also this is all done on the sensor. So you can just plug in the video signal to a monitor and you will see the overlays. Okay, that is an example. Like I said before, it's critical that it's very accurate. You see it's the driving path is free. You see it's only on the sides here that there are objects. So yeah. And in this case, our point was a bit, how can we make this rather easy? So that it's easy useful, because it should be that you don't need to be a vision expert to use such a system. So idea is to make some set out of it where you don't need to be experienced in vision. And we try to do this, and points are that all hardware we use for that set is specifically developed for harsh environments, so it can be used on construction equipment. That we have a package which is easy to set up, so and easy to also to retrofit on machines. This is an example where we put it on a wheel loader here, and you see how the visualization may look like. So the object is highlighted, you get the distance information, and the color of the frame just indicates if it's zone 1, 2, or 3. So that would be the implementation we have done, and it should be easy to use.